Should we put an iron corner?
I don't know.
There you go.
Dramatic zoom. Okay.
Cool. So we're going to, following on from what we did yesterday, right? We're going to have a look at what happens when you open the switch in an LR circuit. So if the switch has been closed for a long time, after a long time we're going to have 0 volts on the inductor because the current's flowing through it freely and there's a magnetic field that's set up inside that inductor. We've got all of the supply voltage showing across the resistor because there's 0 volts on the inductor, and we know that voltages around a loop add to 0. And then at T0 we open the switch. What we're going to think about with an open switch is that an open switch, even though an ideal open switch has infinite resistance, in reality an open switch just has a really high resistance. And in fact that's something that we're going to overcome, because the thing that's going to drive the phenomena of opening the switch is that the inductor is going to induce a voltage that, even though it's only for a moment, keeps current flow constant. And so we're going to see sparking across the switch. We're going to see electricity flowing through the air as the switch is opened, because the inductor induces such a high voltage that it continues current flow. So let's have a look at what that looks like if we graph it up. So before we open the switch, the inductor voltage is 0 and the resistor voltage is equal to the supply voltage. And then at the instant we open the switch, that inductor voltage jumps up to a value far higher than the supply voltage. So this is the same kind of phenomena that we use to generate sparks, like in the spark plugs in your car, or to make an electric fence give the sheep a reason not to nibble the grass on the wrong side of the fence. So you get a really high voltage because the inductor is going to induce a voltage great enough to keep current flowing, even though there's a gap in the circuit that's got resistance of mega ohms. And so that's going to go up really high, but because the inductor voltage has gone really high, we know that's a really high amount of energy per charge. We've only stored a finite amount of energy in the circuit, and so as it collapses, that collapse is going to be a really steep, quick collapse. We're still going to have a time constant, tau, which is going to be L upon R. That R is the total resistance of the circuit. So because that total resistance of the circuit doesn't just include the resistor, but it includes the resistance of the open switch as well, that R there is a really big value. And that means that tau is going to be a really short number. You can see it compressing right up against T0. And that makes sense also because of the conservation of energy. Like we've only got a certain amount of energy stored in that inductor. It induces a really high voltage, but it can't sustain it for a long time. What we're seeing, that time constant, is the time for a 63% change in the inductor voltage. In other words, to 37% of VL max, whatever maximum voltage it rises up to. And the reason that this voltage is induced across the inductor is to keep current flow constant. And so that means that for a moment, after the switch is opened, the resistor voltage is going to stay constant because V equals IR. If I stays constant, then the voltage of the resistor must stay constant, but then very quickly drops off to an asymptote. And so we can see that the resistor voltage is a bit less than the inductor voltage because the inductor voltage has to cope with the fact that it's driving current across the switch, across that open switch, which is a very high resistance, as well as pushing it through whatever the resistor is. Almost always, the open switch is going to be a much greater resistance than the resistor we've got in the circuit, and so almost always, most of the inductor voltage is going to be seen here, and only a very small amount is seen across the resistor. Total circuit resistance in the loop with the inductor in ohms. Obviously, if you have to apply the Kirchhoff's laws to solve a circuit problem, you're going to have to apply them with the inductor in place. But just be aware that it's not just the resistance of the resistor, but it's the total resistance that has to be overcome to make current flow. So the collapsing magnetic field in the inductor is inducing a really, really big voltage across the inductor to try and keep current, or to keep current flow constant. That's the critical thing that has to happen, is that current flow is constant. So it's very different, the behaviour when we close the switch. The inductor voltage opposes the change in current, so it's just equal to the supply voltage, and then drops away as current begins to flow. But when we open that switch, the inductor voltage is much, much, much greater than the supply voltage.